We use the term hurricane when we have a storm in the Atlantic or the East Pacific. So Atlantic or East Pacific, excuse me, East Pacific, you're going to have a hurricane. A typhoon is going to be down here in the West Pacific. A cyclone is going to be in the Indian Ocean and down here in the Atlantic. Oops, I can't see my screen. Hold on a second. Australia. So, whenever you see these three terms, hurricane, typhoon, or cyclone, they actually mean the exact same thing. They're just occurring in different parts of the planet, but they're the same. They are large storms, huge, the most violent of all weather phenomena. Just to give you some example, 1972 Bangladesh, 300,000 people to 500,000 people died. That's remarkable for a storm to kill so many people. 1991 Bangladesh, 70,000 people died from floodwaters alone. So these are real dynamic storms, they're deadly storms, and the fact of the matter is people should be concerned. And when we talk about the recent hurricane, you've got to be concerned about it because if you've got a storm that starts off as a Category 5 and heads towards Florida, that's a big deal. And we'll talk about what that Category 5 means in just a second. So when you take a look at these locations, the next question becomes is what do all of these settings have in common? Well, the first thing you'll note is that they're on relatively low latitude. In addition to that, you'll find that most of these storms are found here on the western side of oceanic basins. That's going to be predominantly due to the easterly trade winds pushing all of this energy and moisture in this general direction. You'll notice that you've got these storms here in the East Pacific. That's going to be due to the the equatorial countercurrent, which we'll talk about in just a second. So we know that the majority are along the western portion of ocean basins because of these easterly trade winds. What else do they have in common? You'll notice that you don't see any of these storms on the equator. And you don't see any on the equator because you need the Coriolis effect because you have to have wind shear and rotation for these storms. Well, Coriolis at the equator, if you guys recall, is 0. Coriolis increases as you go to higher latitudes, north and south. And so here, because there's no Coriolis on the equator, you're not going to find any of these storms on the equator. The next question, what else do they have in common? Well, temperature is hugely important. You need to have a minimum sea surface temperature of around 26 degrees centigrade. That is equivalent to around 80 degrees Fahrenheit. And we're not just talking about this temperature at the surface, but you're going down to at least 100 feet or so. So this warmth has to travel down extensively. Well, why is this warm water so incredibly important? It's super important because remember, water holds all of that latent heat. So when heat is in the body of water, and if there's so much heat that the temperature actually increases, knowing that latent heat tends to be hidden within the water molecule, that's a huge amount of energy. And so when you take all this H2O liquid, and if it has a bunch of heat in it, and you know it does because of the higher temperature, when this stuff evaporates and turns into H2O gas, then we're going to be releasing all of this energy. All of this energy. So again, these storms are energy rich, and sea surface temperature being around 26 degrees centigrade is a mandate. And then finally, why are there no hurricanes in the South Atlantic? Well, that's not really a true statement. Hurricanes in the South Atlantic are extraordinarily rare. They just simply don't happen that often, but it could happen once in a while. But we really don't see anything down here because in order to create one of these big storms, you really need to have something called an easterly wave, which we'll talk about in a second. But an easterly wave is an incredibly large, low pressure cell that develops. Right here in the South Atlantic, we really don't have the capacity to create an easterly wave. There's just not enough space for that to occur. In addition to that, the temperatures of the water oftentimes don't get to that 26 degrees. because we don't have enough length here on this equatorial zone for the water to warm up, because most of this is gyre water and it's coming from down here, which is cold, and it doesn't really have the time to warm up over here. So that's another reason we don't see them typically in the South Atlantic. So let's spend a little bit of time talking about these storms, figure out what causes them, why they're so dynamic, why they're so destructive. So again, we start with easterly wave. A hurricane itself begins as a tropical disturbance. That's basically a thunderstorm with little to no rotation, and it forms predominantly from an easterly wave. And let's look at Africa as an example. You have the trade winds flowing off of Africa, and they flow here toward the oceanic waters. You'll recall that when we took a look before at isobaric maps, an isobaric map is going to be a map where you've got lines of isobars. And isobars are lines of equal pressure. If you have an easterly wave, what tends to happen is there's so much of a low pressure flow going into this particular area that isobars actually collapse on each other. And to make this as simple as possible, let's just say, for example, the air pressure here is 1,000 millibars. And this one is 996 millibars, and this one is 992 millibars. So we're seeing these bars of equal pressure on this map. What an easterly wave is going to do is take this low pressure and have it encroach upon this low pressure cell, and this whole area becomes 992. In other words, the low pressure system just simply expands because of various conditions on the ground. And these conditions can be due to an increased flow of air, that's low pressure air. It could be increased temperatures. Maybe there's a flow of hot air coming off of Africa and it flows into this colder water. That creates more of an instability because the water is cold and this air is hot. And so now the air has much more rapid uplift. That creates a closing of these isobars, also creates the easterly wave. So that's how you would start a storm like this. So if one isobar closes, that's what's called a tropical depression. If the wind from that tropical depression intensifies to 37 miles per hour, now you've got a tropical storm. If that wind intensifies to 74 miles per hour or greater, now you've got yourself a hurricane. So again, these storms generally start with these easterly wave patterns. Now, just because you have an easterly wave doesn't mean that you're going to form a hurricane. But this is what you need to start a hurricane. Now, I tell you this because the hurricane that hit Florida is relatively unique. Because here's North America, not a very good North America, but here's the Gulf of Mexico. And that hurricane started here and went this way. There wasn't a huge expanse to create an easterly wave. And so in here, we didn't have an easterly wave. We had an incredibly large low pressure cell develop due to airflow coming into the Gulf of Mexico and incredibly high temperatures of the water, which led to a rapid low pressure cell, which created the formation of a depression, which led to a tropical storm, which led to a hurricane. This guy here was a category 5 before it hit the coastline and was a category 4 when it struck land. Those categories mean something, and we'll talk about what that is in just a second. Okay, so that's how we start one of these storms. Now, there's some more questions. Let's say that we have a hurricane developing here in the Atlantic, and it's traditionally going to flow this way, flow up the eastern seaboard, and then maybe flow up into the North Atlantic. That's the typical path to which a hurricane here will take. You can see this satellite image, by the way, and you can see the Great Gulf Stream. And that's exactly what this is. It's the Great Gulf Stream, which is this warm water flow. So here's our hurricane, starts here with an easterly wave, flows in this general direction. It's moving with the warm waters of the Great Gulf Stream, maybe hits the eastern seaboard and gets redirected to the north because it's simply following that warm water current. Question: what happens when the hurricane hits cold water? Well, remember, 26 degrees centigrade is necessary for a hurricane to form. So if you take a hurricane and you hit it in cold water, it'll immediately begin to dissipate. This is one of the reasons why the storm stays within the Gulf Stream, because it wants to stay in that warm water. It continually feeds itself. What happens when the hurricane hits land? Well, the same is true. When you hit land, you're now removing it from the source of energy, which is that warm water. In addition to that, the land surface itself has high surface friction, which slows down the air flow, which slows down the wind, which means if you're no longer at 74 miles per hour, you're no longer a hurricane. So what happens when a hurricane hits cold water? What happens when it hits land? You're going to begin to dissipate. Next question, why do hurricanes on the East Coast migrate more north than on the West Coast? Well, we've already established we've got this really nice, great Gulf Stream warm water flow. If you've got a current coming this way, and you have the equatorial countercurrent, which is bringing that warm water, and if you have storm development here, you're not going to go up the western seaboard, because here we've got the cold California current coming down this way. So here's our Cali current, and the California current is nice and cold, and it's going to come this way from Alaska, and it's going to push down any type of current that might be flowing north. So in this regard, you're very rarely going to get anything that hits San Diego. I mean, we had that one storm scare, I think it was last year, and this is something unique for us on the West Coast. Like, we're relatively prepared for earthquakes, but not so much for hurricane. And principally because the cold current from the Alaska region pushes down any storm that might develop down here. And so we had to prepare. We dodged a bit of a bullet in that we didn't get the brunt of the storm, so we had more of a tropical event before it hit us. But if we had had a tropical storm that led to a hurricane, that would have been a problem. We just don't have capacity for it. There would have been a lot of flooding, a lot of damage. Our homes aren't built to withstand hurricane storms and hurricane winds. Unlike the East Coast, where they've got brick houses, we've got wood houses that are more flexible for earthquake activity. So it really could have created a lot of damage, imagining that a 74 to 200 mile per hour wind was going to cross our path. So these are the answers to these three questions. Now I've got another question, and it's involving Jupiter. So here's the great red spot on Jupiter. This thing is really big. You can stick like 3 Earths in here, if not more. So that's how big it is. This great red spot is a hurricane-like storm on Jupiter, and it's lasted for more than 300 years. Put this in perspective. A hurricane-like storm on Jupiter has lasted for more than 300 years. A hurricane on Earth will last about a week. So with this in mind, and knowing what creates the dissipation of a hurricane on Earth, can you use some comparative planetology to tell me a little bit about Jupiter? And the answer is yeah, you actually can. Now, please don't tell me that Jupiter has land or Jupiter has water. Those are all assumptions that are too far. But what you can do is say, you know what? If the Earth was all water, then a hurricane wouldn't dissipate. If the Earth was all land, and if you still had hurricanes, then it wouldn't dissipate. In other words, a homogeneous surface would encourage the continuation of a storm like this. A heterogeneous surface, like what we have on our planet, can lead to dissipation. So, if I ask you, tell me something about Jupiter based upon the great red spot, you can probably tell me, well, you know what? Jupiter is probably a homogeneous surface. And you would be absolutely correct. It is one big ball of gas. And its rocky interior, probably the size of Earth, way down here in the core, is sort of nothing compared to the enormous atmosphere to which Jupiter is. And because Jupiter is this homogeneous gaseous planet, you can have storm systems that last hundreds of years on the planet. And it's not just the Great Red Spot. This little guy down here has been around for a long time as well. You see this on Neptune too. There's the Great Blue Spot on Neptune, which is very similar to the Great Red Spot on Jupiter, but it's a different color because it's more of a methane gas versus this, which is more carbon dioxide and sulfurs. But you don't need to know that. You just need to surmise that Jupiter is probably a homogeneous surface. Right? Okay. So let's take a look at the storm itself. Winds are pretty amazing. Out here, you're looking at winds that are about 74 miles per hour. But as you get closer to this eye wall boundary, winds are now going to be in excess of 200 miles an hour. That's super fast. Like, even 74 miles per hour is fast. If you drive your car and you roll down the window and you're driving 74 miles per hour and you stick your hand out, not your head because that's dangerous, 74 miles per hour is a lot. Well, imagine going 100, 140, 150, 200. That is a super fast moving flow of air. And if your house gets hit by 200 mile per hour wind, our houses are going down. That's just enormous amount of energy and mass that's striking something. So the question becomes, why is the wind so fast here, relatively slower here? Well, keep in mind the storm system itself is a series of low pressure spirals. So air flows into the low. It's moving in a circular format like a mid-latitude cyclone, but bigger because of the Coriolis effect. And it's a series of spiral bands that are doing this. It's a series of low pressure systems within a major low pressure system. It's bizarre. And all this air from the low pressure system goes to the upper atmosphere. And when it gets to the upper atmosphere, it's got to go somewhere. So a lot of the air is going to flow outward like this and then feed back into the system and feed the low pressure cells. But some of the air will also come this way and converge together. And the only place for it to go is going to be straight down. And this is the high pressure system within the storm. And that's what the eye of the storm is. The eye of the storm is a high pressure cell. And as we know, high pressure air tends to be dry. Low pressure air is wet. And so the eye of the storm is fair weather, dry conditions. And we're looking at maybe about a mile or so in diameter. It's pretty small and tight, whereas the entire storm itself might be about 350 miles in diameter. So that eye is pretty small. But remember, what creates the strength of a wind? The strength of the wind is dictated by the pressure gradient force. And the pressure gradient force is the change in pressure divided by the change in distance. So here's our high pressure cell. Here's low pressure, low pressure, low pressure, low pressure. And the distance is getting further and further and further. So the closer you get to the eye wall boundary, then you are maximizing the pressure gradient force. So the pressure gradient force is the strongest at the eye wall boundary, and it's the weakest at the furthest spiral from the eye wall boundary. That's why the winds here are around 74, and the winds here can be on the upside of 200. Now, let's say for sake of argument that you were in the path of the storm and you were unfortunate enough to get in the path where you have the eye cross you, because it's actually not cool. Because if you cross the eye, then you'll cross the eye wall boundary and you will suffer the 200 plus miles per hour wind. Let's say you hit the eye In the eye, it's fair weather conditions. You might actually have a bunch of birds flying around. The birds are stuck. They're not getting out of the storm system because if they fly here, the winds are too strong. So you might see a bunch of birds that are trapped within the eye in this fair weather condition. But that experience is going to be a short-lived experience because as the storm moves, you're eventually going to hit the other eye wall boundary and get smacked with air coming in the other direction. It's crazy. It really, really is crazy. Now, these winds are spinning at 74 to 200 miles per hour, but the entire storm itself is moving at about 30 miles per hour. So we see our two recent hurricanes, Helene and the one that just hit Florida. And you're looking at these storms and they're moving at about 30 miles per hour. And here's the one coming off Florida. And it starts here in the Gulf of Mexico, and it starts as a Category 5. Oh my gosh. Category 5s I'll show you to be really damaging in just a second. But it hits the west side of Florida, and now it drops to a Category 4. It goes over Florida, and now it's a Category 1. And then it goes across, it doesn't sit, and during the course of the night, the entire storm goes across Florida. They dodged a bullet. And they dodged a bullet because a Category 1 that is quickly passing is much safer, obviously, than a Category 5 going slow. So again, if you were to watch the news, they're probably going to tell you that this hurricane that crossed Florida, they dodged a bullet. And I haven't watched the news, but I can only assume that that's what they are saying. Now, the enormity of this energy is crazy. The energy released in a hurricane is greater than the annual electrical consumption of energy in the US and Canada alone. That's amazing. The sea level pressure can drop. Normal sea level pressure is over 1,000 millibars. But these storms, the sea level pressure drops to around 870 to 990. Well, keep this in mind. If you have sea level and you've got 1,013 millibars pressing down, if you release that pressure and you drop it to 870, that means that the sea level is actually going to rise. Sea level is rising. Couple that with huge winds pushing water on the coastline. That creates something called a storm surge, and a storm surge itself can literally wipe out coastlines. It's impressive. Lifespan, maybe about a week if you're lucky, because sometimes these storms just sit, and if they don't move, and if you're beneath it on some type of island, for example, in the Caribbean, you're screwed, and it's a big, big problem. By the way, a real quick aside. You know, I'm a political junkie. I'm really into politics. It's hard to turn some of it off no matter how much we want to. And, you know, you've got Marjorie Taylor Greene out there with conspiracy theories that the US government can create hurricanes and they're doing it for various reasons. And then you've got other people on the far right saying, why don't we just drop a nuclear bomb in the middle of a hurricane? Shouldn't that destroy it? Without consideration of the consequences of a nuclear bomb being exploded in a hurricane. The answer, though, the short answer is no. You can't drop a bomb in a hurricane and have it die off. It doesn't work that way. And the danger and destruction associated with that, even if it could work, wouldn't be worth the dime. So you see a lot of this going on, and my encouragement for you is if you have any questions, just please feel free to ask it, okay? So there are some things you can do and most things you can't. All right, so let's take a look at damage. So let's say, for an example, we've got a hurricane and it's approaching a coastline. Now, you'll notice too that we've got this storm and it's rotating in this nice counterclockwise direction if we're in the northern hemisphere. It's ripping at about 30 miles per hour. The spin rate is around 74 miles per hour on the outside. As we approach the eye wall boundary, we're looking at about 200 miles per hour. Right here, we're going to get massive storm surge. The massive storm surge is the piling up of water along the coast via both the winds and the lower air pressure. And remember that lower air pressure, 1 centimeter rise per every millibar of decrease. So your water levels can rise 2 to 7 meters, which is 6 to 25 feet. It's amazing. Like I was just reminiscing today with a group of students. I grew up in Southern California. My beaches that I grew up on were Huntington Beach and Newport Beach. And so I would frequent them a lot. And I would body surf a lot. I wasn't a surfer, but I was a body surfer. And I remember distinct days going to Huntington Beach and body surfing and getting smashed by waves. Like literally smashed by waves and getting dragged in the undertow. And I would think to myself in those days, man, that was a big wave. Then I would come out of the water and I would look at the ocean and the wave was maybe 3 or 4 feet. And so 3 or 4 feet is not that big unless you're in the water, then it's huge. Well, imagine 6 to 25 feet, 25 feet in particular. That is an enormous wave. And what a storm surge is, it's essentially a crest of a wave, but without the trough. It's just an enormity of water that smashes onto the coastline. The amount of destruction is amazing. Okay, so let's look at the categories. And as we look at the categories, this is going to indicate why Florida got lucky to a certain extent. Category 1, your winds are about 74 to 95 miles an hour. Your pressure is maybe 980 versus 1013. Storm surge 4 to 5 feet. Damage is minimal. Now, of course, we all say this, we're not in the storm. Minimal damage becomes relative dependent upon your house. But a storm surge of 4 to 5 feet is going to create some flooding, but it's not going to create massive damage where you're completely eradicating an entire community. Category 4 is much bigger. The damage is extreme. Storm surge can get up to 18 feet. Winds can get up to 155 miles per hour. That's crazy. So the hurricane last night when it crossed Florida, let's draw Florida as best we can. It hit the west side of Florida as a category 4. This was the damage potential over here. By the time this hurricane got right here, it's a category 1. So remember, what dissipates a hurricane? Either going over cold water or going over land. And in this case, the hurricane went over land. It dropped immediately down to a category 1. That's why Florida dodged a bit of a bullet and it got lucky. With Hurricane Helene that went up the eastern seaboard and hit Georgia and North Carolina, they weren't as lucky because when the hurricane hit them, I believe it was like a category 3. So this area in Florida, they got pretty fortunate and it stayed category 1 until it hit the Atlantic. And then it stayed category 1. So it didn't grow, it didn't increase in size. That's why when we take a look at Florida, the damage was relatively minimal compared to what it could have been. In addition to that, they were fairly prepared for energy outages. In fact, there was people from even as far as California, electricians and search and rescue people that flew out to Florida in preparation. They really thought it was going to be huge, like a category 4 or 5 going across the entire expanse. So they really did dodge a bullet, proverbial bullet, of course, when it came to this hurricane. There's one more thing I actually do want to talk about tonight. One of them is lightning. And lightning is a really interesting phenomena that develops in thunderstorms. I'll have you all read about thunderstorms. It's not like particularly difficult to see how thunderstorms develop and that stuff. And there's some really good stuff on our Canvas website that talks about that. But what's more interesting and maybe a little bit more challenging to comprehend is the development of lightning. So let's just briefly talk about that. And then I'll let you go. I'll let you out of here by around 5:30 or so, if that's okay. So thunderstorms themselves occur about 40,000 times each day around the world. Like that's a lot, but that's like one of the biggest type of storms that we have on the planet. Lightning and thunder are both byproducts of these storms, causing electrical disturbances, fires, etc. About 200 people are killed by lightning. There should be no E there. Each year in the US and Canada alone. So even though there's large populations in the US and Canada, having anybody die by a lightning strike is still pretty crazy of a phenomenon. 80% of lightning results within the clouds and is called cloud-to-cloud lightning. 20% is cloud to surface and surface to cloud. This, of course, is the pretty stuff, but we actually see more lightning within the cloud itself. So the question becomes, what creates the lightning? Well, the lightning is a result of charge separation. As it turns out, air is a really poor conductor of electricity. Therefore, in order to even have lightning where you're actually closing the gap, it takes a tremendous amount of electricity to connect the ends. And we're talking about millions of volts. So just to give you perspective, let's say that we've got a cloud. In this cloud, we're going to see a charge separation, meaning we might see a bunch of negative ions down here at the base of a cloud. We might see a bunch of positive. But again, air is such a poor conductor of electricity, it doesn't really matter. But if this gets huge, then the amount of electricity can actually jump the air and create sort of a virtual wire in the sky, and that's what lightning is. So it's a tremendous amount of energy separation build up in the system itself. The question becomes, what creates this charge separation? So very quickly, let's talk about that. One idea, here we go. Let me put this up here. So in our clouds, here's our cloud. You're going to have positive charges accumulating in the upper reaches. You're going to have negative accumulating in the lower reaches. What creates the charge separation? Well, one idea is called the thermal electric effect. And the thermal electric effect is going to involve ice crystals, hail, and even water droplets. So let's take a look at how this works. Let's say that we have a thunderstorm cell. This thunderstorm cell is going to be a huge cumulonimbus cloud. Cumulonimbus cloud is a rain producer with huge vertical development. That's the cumulus name, huge vertical development. Now we know that in this cloud we'll have the lifting condensation level, the LCL. But also in this cloud, you'll have the freezing point. So if water gets above the freezing point, the liquid will freeze and create a little ice piece or an ice crystal. So this is what we have in a thunderstorm. In a thunderstorm, you've got a downdraft. And the downdraft is taking a bunch of rain. So you're going to have a rainfall associated with this flow of air coming down. The flow of air coming down is balanced by a flow of air coming up. That's the low pressure system. So the low pressure system lifts air up into the sky. If the air gets above the lifting condensation level, we get a cloud. If there is huge amounts of uplift, then this cloud can develop huge vertical development, flow above the freezing point. Therefore, any moisture up here could in fact turn into ice. And so you're going to get a bunch of rain in this thunderstorm. This rain creates a downdraft, and as a matter of fact, if you're standing here, you're going to get a bunch of showers on top of you, but you'll also feel the effect of air being pushed down and feel this downdraft of flow. Okay, so this is our thunderstorm rain cell where rain is coming down. Now, air though is continuing to push up. So remember, this updraft is really strong. So let's say for sake of argument, we have an updraft. Let's say that some of this moisture coming down is caught in the updraft, and so before it can leave the cloud itself, it goes up. And let's say that the updraft is so strong that the moisture goes above the freezing point. Well, now we form a ball of ice, and let's call this ball of ice hail. Hail is heavy, and so it's going to start falling down the cloud. This hail is now going to run into uplifting ice crystals and water. And when it does, we're talking about static. So if you've ever taken like a balloon and you rub the balloon on wool, and then you put the balloon above your head and your hair shoots up, that's static electricity. And what you're essentially doing is you're ripping off electrons from the item going down. And so, actually, no, let me rephrase that. You are having ice or water go up, it's running into the hail ball going down. You're basically ripping off positive charged elements from the hail that's going down. And by the time the hail is down here, you've got an overall negative charge. So that's what static is. You're dragging your feet and you're dragging ions from one, and you're basically creating an imbalance in positive and negative. So now our ice crystal goes up and it has that positive on it, and our negative is going down. Well, this can continually happen, and if this cloud is absolutely huge, you'll have updraft and downdraft continuing. By the way, when you've got your major thunderstorms, these hail balls can be the size of softballs. Like, they can be absolutely huge. I was driving through Denver as a kid, and I can remember clearly huge hail balls hitting the surface of our Volkswagen van. And Volkswagen vans in the 70s and 80s was like sheet metal. So I remember clearly as a young kid, hail balls the size of softballs denting our car. Like, it was pretty impressive. So again, we have these big charge separations in the cloud. So we've got a bunch of negative down here, a bunch of positive up here. This movement within the system creates the thermal electric effect. And if there's so much charge separation, the energy is going to jump. And when the energy is jumping, that's the thunder. Excuse me, that's the lightning. And so again, all we're doing is closing the gap. What's interesting is if you've got a bunch of negatives at the base, then down here, let's say you've got a tree or a series of trees, positives from the ground are going to go up to the tree because they're attracted to the negatives. And any negatives that might be down here sort of repel away. So this whole area becomes very magnetic. And when we talk about cloud to ground lightning, it's because now we're jumping again. The charge separation between the base and between the trees and the ground becomes big enough that we can actually create a lightning event that hits the ground. So that's how we do this thunder. And you might say, well, okay, well, lightning. And you might say, well, what's thunder? Well, this air is superheated. Like, it's superheated. The air is like heated to about 30,000 Kelvin, which is over 30,000 degrees centigrade. That's tantamount to a 100-watt light bulb at 20,000 amps, which is crazy amazing. And so because that air gets heated so fast, it has rapid expansion. That rapid expansion, that is the supersonic movement of air. It's now going faster than the speed of sound. That creates the sonic boom. So that's what thunder is. So the lightning occurs, the thunder occurs, that's your lightning event. So again, you get your thunder because the increase in temperature causes the air to expand rapidly. Sound, by the way, travels at about 0.3 of a kilometer per second. Light, on the other hand, travels at 300,000 kilometers per second. So light travels much faster than sound, but we can use that to figure out how far away the storm is, because you can use this little equation. Distance to your storm is the seconds between the stroke and the thunder. And you divide it by 3 for kilometers, or you divide it by 5 for miles. So let's say that you see lightning. You see the lightning, then you start counting 1001, 1002, 1003, 1004, 1005, boom. You hear the sound of thunder. You know that you've got 5 seconds divided by 5, so your storm is about 1 mile away. That's how it works. Now, you can only use this up to a certain point. If the storm is really far away, you will see the lightning, but you will not hear the thunder. And it doesn't mean that the thunder didn't exist. It just means that the sound itself is absorbed or refracted away by the atmosphere because that storm is so far away. We would call that heat lightning. So heat lightning, you can see the light, but you can't hear the thunder, and it's just really far away. So if we talk about lightning safety, where should you be? Well, you don't want to be around water. And I have to say this, it's not because water is a good conductor of electricity. Water itself is actually a piss poor conductor of electricity. The problem is the water that's in a lake or a river or a bathtub for that matter, or a swimming pool or a hot tub is not pure H2O. It's H2O plus a bunch of minerals and other stuff. It's the minerals and other stuff which is a very good conductor of electricity. So if you find yourself in a body of water and lightning hits it, you're in trouble. So don't be in water. Don't be on a golf course, because golf courses have a bunch of trees, and then you're holding a lightning rod called a golf club. So not a good idea to be on a golf course. But what about a car? A car is actually one of the safest places to be during a lightning event. So here's your car. And if lightning hits the car, it'll go across the car surface, hit the rubber, and it's grounded out. So being in a car is actually extremely safe during a lightning event. So that's probably where I would suggest you go inside of your car. What if you have 2 people standing outside and one is taller than the other? Is the one who's taller in more danger than the shorter one? I think your intuition would say the taller one's probably in a little bit more trouble, but that's not necessarily the case because the difference here is only like maybe 12 inches at most. I've got a meteorology book, and it has a picture of 2 brothers, and the picture before is them both smiling and having a good time. The picture after is them not smiling and having a good time because the younger brother actually got struck by lightning and the older brother did not. So standing by somebody tall isn't going to save you. And being under a tree is not going to save you. There's a lot of cellular tissue here. This tree is most likely than not going to get struck, and a branch could fall off and hit you in the head. That's not a good place to be. What else? What other information can I share with you that'll save you? If you got struck by lightning, the odds are you're probably not going to die. Even though it's a 100-watt light bulb at 20,000 amps, that's actually safer than a 100-watt light bulb at 1,000 amps. And I'll tell you why. If you get struck by a 100-watt light bulb at 20,000 amps, it's going to blow you across the street. So maybe you'll have some broken bones and some headaches. But if you stick your hand on a 1,000 amp, 100-watt energy, like a battery, you're going to stick to it. And the reason why you're going to stick to it is because the electrons are going to flow from this source and into your system, and you won't be able to break away. And you'll probably fry from the inside out. So getting struck by lightning, although dangerous, is probably less dangerous than less current, if that makes any sense. And there's no real bearing for that, otherwise it's just sort of cool to know.